So let's turn now to what is science. I want to make it clear that scientists love to talk about science. They love to talk about doing science. They love to talk about the process involved in science and the reasoning involved in science. They love to talk about the results of science. They love to tell the story of how things work and how their little bit of science sheds light on how the world functions. However, if you ask 5 to 7 scientists, like these blindfolded scientists here feeling the elephant, if you ask them what is the definition of science, you might get several different definitions because there's no one consensus definition of science. Each person sees the process of science from their little corner. So it's a rope, it's a wall, it's a tree, it's a snake, it's a spear, it's a fan. It just depends on what sort of science any one individual's involved in, and that reflects on their definition of what science is and how it functions and its importance in the world. So ask 5 scientists what science is, you might not get one single definition. However, the American Association for the Advancement of Science has given a basic definition. Their definition is a process through which people seek a better understanding of the world. So it is a process, it is a series of steps with a goal of understanding the world around us. Science explains the physical phenomena, which is a big word for just the physical entities that we see around us, the physical realities, through the formulation of theories that then are tested and confirmed through empirical, that is, through repetitive observation or experimentation in the real world of nature, of what we find around us. However, their definition here also limits science to what can be seen, heard, tasted, smelled, or touched. So the operational aspect of science is that science is a process. It involves controlled experimentation. It is limited to the physical world. That is a major limitation for science because there are things that are real which are not physical. And that these experiments lead to explanations about the physical world. So the process may raise additional questions and the cycle starts again. But let me give you one example of a particular kind of an experiment. This is a clinical trial or a clinical experiment involving real individuals. This is the kind of science that's done in medicine. This was a trial that was done enrolling people with a disease called chronic lymphocytic leukemia into a controlled experiment where some people were randomized or entered into one arm of the trial or the other. Each arm was to get a particular kind of chemotherapy. So you can see the difference between the two arms is the presence or absence of a compound called rituximab, which is an antibody. These are chemotherapy-type infusions. The patients are then followed and observed for how these treatments affect their disease. So this is a tightly controlled experimentation involving humans as the subject. The results of this trial at 42 months are shown in this graph. So you can see how science then takes the information that's gathered over years and plots that on a visual representation so that you can at a glance tell if there's a difference between the two kinds of treatments. And it turns out in this case there are, and there's clearly a difference or a separation in the curve so that what's called the median progression-free survival is the difference between these red and blue curves at the 50% level, when half of the patients have relapsed. And that occurred at 31.5 months for the blue arm versus 39.8 months for the red arm. And that difference is statistically significant. So there's a measure of whether this difference is due to chance or it's actually due to the presence in the experimental arm of the rituximab antibody. And it turns out this is statistically and clinically very significant. In fact, the addition of rituximab has now become the standard of care in this disease state. So that was, again, one example of how science can be done. And so if we go back to just thinking about what the scientific method is, there's two representations here. On the left, it's represented as more of a circle, or if you could think of it as a crank, defining a problem, doing experimentation, laying out the results and communicating the findings in scientific journals for repetition and for criticism. And then you start the process over again, and you just keep cranking, asking additional questions. On the right, the scientific method here again begins with observation, hypothesis, and experiment, and it shows the cyclical nature by the process of finding a result and whether that result is consistent with the hypothesis, and revise it and try the experiment again. Or, from the standpoint of other individuals, does the evidence support or contradict a larger hypothesis, and can that be repeated by not only yourself or your group, but others around the world, because science should be the same and should be repeatable around the world. And if so, that evidence may be incorporated as part of a theory that's a larger explanation of why things are the way they are, but that also leads to predictions and further experimentation. So predictions are a key component of what the scientific method is all about. In addition, there are other types of science. There are historical sciences and observational sciences. Now, these are very different fields of what I would call, quote, science, because historical science is defined as studying past events. And it's difficult to do science on things that have happened historically in the past because those events can't be repeated. One can, however, do science on artifacts and other things that have come from the past and validate their dates and those sorts of things. But it involves using the knowledge that we have to tell a story of what has happened in the past. And you might know this from paleontology, the idea of let's look at these now extinct dinosaurs and try to tell the history of their past life, or forensics. And then, of course, there's archaeology and geology to explain past cultures and how individuals in the past have lived. That kind of science is not the process type of science. It is more an interpretive kind of science that also uses the process to tell a story. Now, sometimes those stories can be rather far-fetched. For example, what is the beginning of the world? What's the beginning of the universe? And scientists, when we talk about these kinds of events that only happened once, and so science really doesn't apply because it can't be repeated and studied in a controlled way, we end up telling stories. This is the story of space, time, and the search for life beyond our planet. And this book begins, in the beginning, there was nothing. It was a nothing so profound, it defies human comprehension. So, first of all, we begin with a philosophical statement, in the beginning there was nothing. It's nice to say there was a beginning, but then to say that there was nothing there so that we can't even comprehend what the beginning was is a little bit difficult to say that fits into science. A long, long time ago, there was no matter, no radiation, and more importantly, space did not exist and time did not flow. And these are quotes. However, no one was there to see nothing or no space or no time. So our knowledge of that is not firsthand. And then suddenly, from nothing, a tiny speck of brilliant light appeared. It was almost infinitely hot. Inside this fireball was all of space. From nothing, something appeared. But we don't know why. We don't know how. And so how can science be done on something that is in the remote past? And how can something appear from nothing? But that's what we're asked to believe in telling the story of the beginning of the universe. That there was nothing and then suddenly there was something. With the creation of space came the birth of time, and the great cosmic clock began to tick some 13 billion years ago. Now, I'd ask you to try to see the difference between the kinds of clinical medicine experimentation that we have discussed and this kind of storytelling about non-scientific philosophy. May be based on some observations of space and inferences, but it certainly doesn't fit into experimental science. Now, observational science is another kind of science which is a valid field where we can't do a controlled observation, but we do want to study causes and effects in the present time. And we often use this in medicine as epidemiological type studies or long-term studies of correlations between human behavior and disease. And that's what happened in this particular trial called the Framingham Heart Study, begun in 1948 in Framingham, Massachusetts. The purpose of this long-term observational study through time was to identify these common factors that contributed to people getting cardiovascular disease over a long period of time. So they recruited 5,000 plus men and women between the ages of 30 to 62 in Framingham, Massachusetts. Then they started their physical examinations and lifestyle interviews. Now, one of the great demonstrations of the Framingham Heart was this risk score, designed to tell an individual what their particular risk is of developing cardiovascular disease within the next 10 years. And the factors that go into this calculation of the risk score come directly from the results of the Framingham Heart studies. That it matters whether you're male or female, it matters what your age is, it matters whether or not you have diabetes, it does matter whether you smoke, whether you have high blood pressure, and whether that is treated or not. Your cholesterol levels of HDL and LDL do matter, but in a calculation then they can give an individual a sense of whether or not they are at low risk, medium risk, or high risk within the next 10 years of developing cardiovascular disease. And therefore the physician can counsel people about how they might change their behavior and their diet and exercise. Other major contributions from Framingham include the observations that cigarette smoking increases the risk of heart disease. These are things that we take for granted, but scientifically were not known until the results of Framingham began to come out. Now, these are correlation type studies, not ones that you can say there's a proven cause and effect, but there is an association between cigarette smoking and heart disease. Now, subsequent studies can show more of a cause and effect. And these types of observational science are valid within certain limits. So science is an operational process using controlled experimentation of the physical world, leading to an explanation of why things are the way they are. But by and large, operational science is done now in the laboratory or with people in real time. It is observable and repeatable. Now, science in general can also blend into technology. And there have been an incredible array of achievements of science over 600 years. And so the first one, we can just think of here would be the light bulb. Thomas Edison, the development of the light bulb, development of electric power, development of the infrastructure for radio, development of plastics surrounding radio, development of electronic components for television, development of broadcasting, development of advances in flight that allow us to travel around the world and navigate and communicate around the world with geosynchronous satellites. We have the development of the computer chip, allows the development of smaller and smaller computers, including handheld computers that we now call cell phones. And in medicine, vaccines have saved countless lives over generations and almost eradicated many, many diseases around the world. And then over here on the right, the artificial heart serves as an example of transplantation medicine or orthopedic medicine, that we could replace a heart, we can replace a lung, we can replace a liver, we can even replace joints. And then, of course, the achievement of landing people on the moon and returning them. It was a tremendous scientific, technological advancement that had ripple effects all through the world of science. So these are just a few of the incredible achievements in everyday life that are the results of the scientific method, the scientific and technological process and progress. By no means does this even scratch the surface of all the laboratory science in physics and chemistry and biology and medicine and all these other types of areas where incredible advances in understanding how the world works have been achieved. Now, scientists are also concerned, because of the impact of many of the discoveries have had, they are concerned about what their public face is. What do average people think of scientists? And so typically, you can think of scientists as individuals like these in lab coats looking at little experiments. But scientists are not just found in the laboratory. For instance, this is a marine biologist, a scientist who studies oceans and the life in the oceans. These are field biologists studying polar bears. These are field biologists studying life in caves. And of course, this is a typical laboratory. This happens to be a microbiological laboratory with a bench and reagents and various instruments designed to do controlled experimentation. And so it's important for people not to be afraid of science, but to understand that science comes in many shapes and sizes, and many types of people do science in many, many different ways, and that it is not just one static definition. Now, there are also some attitudes behind that public face of science. For instance, one attitude is just trust me, I'm a scientist. I know more than you do about this issue, and you should trust me and my opinion and my judgment. And you should trust me, or you can trust me, because I am completely objective in my interpretation of the data. And objectivity is one of those areas where you don't want to allow what are called biases color how the data are interpreted. And those biases can be political, they can be financial, they can be religious, they can be philosophical in the interpretation of data. So objectivity is important. And so the scientist says, you can trust me because I am completely objective. And the scientific method is a totally rational method. There is no wobble in the thinking around science. It is a tight circle of reasoning. And therefore, what I would derive as scientific truths are superior to what you might call religious or philosophic truths, which are, by definition, irrational. So now you begin to see the attitude of my work is rational, your thinking and belief is irrational. And that is a tremendous battle. Scientific truths also have disproven the existence of God and shown evolution to be true. And subsequently, since your beliefs as perhaps a religious person are irrational, you are a dangerous person because in that they are irrational, and especially Christian. These are attitudes that are not often expressed, but these are some of the attitudes that are behind the public face of science. And so science is many things to many people, an incredibly powerful tool and process from which people have benefited to great degree down through history. But what does being a Christian have to do with being a scientist? And I want to dwell on that a little longer in our next section.